So we're delighted to welcome you to this seminar, which is sponsored by the Biostatistics and Epidemiology departments here at the College of Global Public Health. We have Chuck Huber here. He's a senior statistician at StataCorp and an adjunct associate professor of biostatistics at Texas A&M School of Public Health. So this is my first time actually meeting Chuck in person, but I feel like I know him really well, and many of you may know him too, because Chuck does all the Stata YouTube videos. So for those of you like me who often use the Stata YouTube channel, Chuck has already taught you lots of things, but he's here today to teach us some more things. His talk today is on causal inference for complex observational data using Stata. Please welcome Chuck.
I feel like I know you as well, just because we have so many mutual friends. So, anyway, thanks. So the way this talk came about is actually because of the YouTube channel. One of my tasks when we do a release is to learn about the new features and then do little 1 to 1.5 minute sort of like a commercial for each of these features. They're not really meant to be tutorials, it's just to give you a gist of what this thing is. And so many of these topics are things that I know literally nothing about, especially the econ features. I'm a biostatistician by training, and so I've had no economics training whatsoever. And so the way I go about doing this is I read the manual first, and I work the examples in the manual, and then I write a little script based on what I've learned from the manual and from working on this. And I show the script to the developer who wrote the thing, and I say, hey, did I catch the highlights? Anything I left out? Anything I said that's wrong? And we have a conversation. And then I work with these scripts. Well, this came across my desk for Stata 15, and we call it ERMS. Its original working title was UberReg. We called it UberReg internally. That was its project name for the 4 years it was under development. But we thought that was kind of weird, especially because Uber has this hard name. And so we decided to call it eRegress, or Extended Regression Models for short, or we now even call it ERMS for short. Anyway, so this came across my desk, and so many of the concepts in this were so foreign to me, things like endogeneity, and I'd heard the terms in places, but I never really given it much thought. And at first, I have to admit, I was slightly disturbed by some of the what seemed like a big leap to causal inference. Causal inference is a new thing for me as well. Again, I come from a traditional biostat, training where cause is a dirty word. Anyway, so, but the more I dug into this, I thought, and this was written by economists for economists, but the more I dug into this topic, I thought, there are a lot of applications for these kinds of methods outside of the world of econ. And I think if I could just translate the language out of econ jargon into something else, maybe other people could see this stuff and use it as well. And so that's what I've attempted to do here, is just yank something out of the econ world and then put it in another form so that it's more digestible to people outside of econ. So the data set that I'm going to use is completely simulated. So don't take anything about the data very seriously, none of the results. And I'm going to have to ask you to make some assumptions or not think too hard about some of these covariates, and I'll explain that shortly. But essentially we're going to talk about endogenous covariates, non-random treatment assignment, and data that are missing not at random that can lead to selection bias. One of the cool things, the cool thing about this is that you can deal with all three of these issues simultaneously. There's really nothing in here that economists haven't been doing for about 40 or 50 years. Maybe the treatment effects is a little less time. So all of these are tried and true methods. What makes ERMS unique is that you can deal with all of these issues at the same time. And that's something very new and unique to Stata and Stata 15. So here's our imaginary scenario. Fictional State University, FSU, before I forget, this is Ermi, our graphic artist. This was a headlining feature in Stata 15, and our graphic artist created this little character, and he doesn't look happy. I've never understood why they didn't make him smiling, but anyway, so this is Ermi. And we sell t-shirts, and somebody even made a little stuffed Ermi, but we don't know how to make those in mass.
It's because the results never come out the way you want.
Yes. That's why Ermi is frowning. Anyway. All right, so the imaginary scenario here is that Fictional State University, FSU, has developed a new study skills program for their students. And the goal of the study skills program is simply to increase the final college GPAs of the students. So this is simple, right? This should be a 2-slide talk. We do a t-test and we're done. How hard can this be? Well, it turns out that there's some twists and turns along the way, and we're going to see what those are. So let's start by just getting to know the data set. I have an ID variable, which is of course fake. These are simulated data. And then I have GPA, which is the final grade point average of the students when they graduate. So when they graduate, we record their final GPA, and that's what that variable is, their final college GPA. Under that is high school GPA, maybe I should move to this side. Under that is high school GPA, and that's their high school GPA that we collected when they applied for the university. Program is an indicator variable for our treatment, whether they participated or not in the treatment, the study skills program. Graduate is an indicator variable for whether the student graduated or not. Not everyone graduates, so we have an indicator for that. Income is the student's parents' income measured in hundreds of thousands of dollars to keep the numbers relatively small. HS comp is a made-up measure for high school competitiveness. Don't think about it too hard. Mine is a fake variable, it's a continuous variable I just made up. It turns out the College Board is actually working on an actual measure for high school competitiveness. So that will be a thing, I think, next year or the year after, but mine is just made up out of thin air. Roommate, this is an indicator for whether or not your roommate is also a student. And that could make a difference in your GPA as well. If your roommate is a student in the same major you are, maybe you study together, that's very helpful. Or maybe you're like me and your roommate was your wife and you had kids, and that can definitely have an impact on your GPA. And then lastly, I have an indicator for scholarship. Did you receive needs-based scholarship money, not academic scholarships? Okay, so strictly needs-based. So that's the data set. That's what we have in here. One of the things I like to do first with my data sets is just look at some descriptive statistics, some basic graphs and things. And one of the first things I look at, is I use the summarize command and look at the number of observations for the variables. Because missing data can be a problem right out of the gate, and that can be a big fork in the road for how you analyze your data. So if I look down the list of observations, all of these variables have 1,000 observations except for GPA, which is unfortunate because that's the variable I'm really interested in. That's my primary outcome. And I only have 792 observations for GPA. Normally, I would also look down the min and the max column here just to double check and make sure that things are within reasonable ranges. I don't have any 370-year-old people or people who weigh negative 99 pounds or kilograms. But these are fake data, so I know they're all fine. Okay, so the first thing I'm curious about is this 792. I only have 792 observations for GPA. So if I tabulate, though, this graduate variable, it seems that I only 792 of these 1,000 students graduated. 208 of those students did not graduate. Well, that explains why I'm missing GPA for 208 students, because I only get their final GPA if they graduate. So that's why I'm missing GPA for 208 students. Another thing I like to do is just do some histograms, and people think this is corny, and people say this is corny to me to my face, but I've also seen some people do some really dumb things with data that have two modes. Skewness, people say, oh, well, OLS is robust to departures from normality, and that's true, and it's fine, but it's not robust to things like U-shaped distributions, which I've seen people use. Smoking, number of cigarettes smoked per day has a U-shaped distribution, so if you ever deal with smoking data. Anyway, so I like to do these histograms first. And this is my GPA variable. Has a nice, freakishly normal distribution, which is a first clue that it's fake data. Because real data doesn't look like that. But anyway, so this is GPA. It has a nice hump-shaped distribution with a mean just north of 2 there somewhere. Another thing I like to do, I like correlation matrices, I suppose. But correlation, remember, only measures the degree of linear relationship between variables. So I actually prefer doing these scatter plot matrices. It's just scatter plot matrix, I think is the command to say that. And what it does is creates a little scatter plot for the variables, just like a correlation matrix, but it's graphical. So if there was a hump-shaped relationship, or S-shape, or U-shape, I can see that. And what jumps out at me here is that final GPA and high school GPA are highly correlated. That shouldn't be a surprise. If you did well in high school, you're probably going to do well in college. So no surprise here. Parents' income seems to be fairly correlated with high school GPA, and parents' income is also somewhat correlated with college GPA. So I'm just filing these things away back in the back of my head before I start building models, just so I understand sort of the basic relationships between these variables. Now my treatment variable, the thing I'm really interested in is did this program improve the students' GPAs? And so this is a tabulation of the treatment variable program. 300 students out of 1,000 actually participated in my study skills program, and 700 did not. This was randomly generated and it just happened to land on exactly 700, 300. That wasn't planned. But anyway, so about 30% of our students participated in our study skills program. So then the next thing I want to look at is just sort of just box plots. I don't even want to talk about means or anything yet, but I just want to look at box plots for final college GPA by program participation. So this bottom box here is for students who did participate in the study skills program, and the top box is for those students who did not. And now I'm immediately panicked because it looks like my study skills program harmed these students. The students who took my program did worse than the students who did not. And that's going to be a really awkward conversation with my dean or whoever is evaluating this program as to how this managed to happen. But then I got to thinking, well, actually I put just a naive regression model with GPA as the outcome and program as an indicator variable. And in fact, it shows that on average, students who took my study skills program had GPAs that were 0.12 grade points lower than the students who did not. So again, very awkward. But then I got to thinking, well, let's take a look at, I'm pretending this is a real study, that's what I'm saying, then I got to think. So then I started thinking, well, let's look at high school GPA, because high school GPA was reported before the students took my study skills program, right? So, and this shows that the students who took my study skills program had lower high school GPAs than students who did not. So now I'm starting to think, well, maybe there's a more complicated pattern here to the relationship between my program and GPA. And in fact, if I do a somewhat equally naive regression model where I have GPA as the dependent variable, and program is my primary thing I'm interested in, but I adjust for high school GPA, now the direction has flipped. So when I adjust for high school GPA, it turns out that my program is actually moved in the helpful direction. Okay? So that's good news. But it also suggests that there is a more complex relationship between the treatment and the outcome. So this is just a tabulation of program and graduate, and I don't think it really helps that much developing our intuition. So last thing I wanted to look at is high school GPA by graduation status. So the horizontal axis here is high school grade point average, and the bottom are students who did graduate, and the top group are the students who did not graduate. And not surprisingly, students who did graduate had higher overall high school GPAs. Came in with a higher high school GPA, you're more likely to graduate in the end. No surprises there either. So, what is the effect? Clearly there's not a simple t-test solution to this question, but how do we go about thinking about the relationship or the effect of study program on students' GPAs? Well, the first thing I haven't really made explicit, other than in the title, is that this was not an experiment. If we were going to do this and design it from scratch, ideally we would randomly allocate these students to the treatment group and the not treated group, but we didn't do that. And there are all kinds of other features of these data that arise because they're strictly observational. I just was walking down the street and found this data set, and I have to find it the way it came. I didn't get to design it in a careful way. And observational data often have one or more of these features. First is something called unobserved confounding and endogeneity. We're going to go through that here in a moment. Non-random treatment assignment or exposure. We didn't randomly allocate these people to get the treatment. We just found them as they were. And then lastly, we've already pointed out that we have some data that are missing. And we need to think about the mechanism by which those data became missing and how that might affect our sample and if it biases it in some way. So let's tackle endogeneity first. Anybody heard of endogeneity or learned about this somewhere? Anybody have any economics training? Okay, one person is willing to nod their head. I won't point at her, but she's not willing to raise her hand. So, what I'm going to show you is tried and true econ stuff. So it's actually good that we don't have a lot of economists in there. So I want to just remind you quickly that high school GPA and final college GPA are pretty highly correlated. And so what we're going to go through is talk about endogeneity and endogenous covariance. So the problem is that we're going to have something called unobserved factors in endogeneity, which can result in one of the causes of this is omitted variable bias, which can result in unobserved confounding, and the solution is to include endogenous covariance in our models. What is this? I'm already starting to use a lot of unfamiliar jargon. Let's back all the way up to grade school and think about what do we really mean when we fit a linear regression model. So linear regression model means that some dependent variable y is equal to all of the factors that could possibly influence y. And some of those factors are observed, and those are the things in our data set, and that's what we're going to use to build our model. And some of those factors that influence y are unobserved, either because we didn't happen to have them in our data set, we couldn't measure them, it was too expensive, we didn't think to measure them, we didn't know we needed to, whatever. But for whatever reason, there are a lot of factors that influence y that are unobserved. Now, if you're like me, you probably bundle those things all together in E and don't give them any more thought. Those are the residuals, they're the error terms. That's a nuisance. What I'm interested in is all this stuff over here, all these beta coefficients and things that I do observe. But it turns out economists spend a lot more time than we do, or that I do, thinking about these unobserved factors. What are the things that get bundled up in that error term? I never really gave this much thought until I started looking at this featuring data and putting together this talk. So we have all these unobserved factors. So let's just define some terms. So endogeneity is defined to be, and this comes from Jeff Wooldridge's intro book on econometrics. I don't know why I have trouble with that word. Anyway, just a stock quoted definition. Endogeneity means that we have an explanatory variable in a multiple regression model that is correlated with the error term. When I first read that, I thought, what? How can that be? Why? How would this even happen? So, in fact, we usually just assume that that's not the case. So what we're saying, endogeneity is defined as we have a covariate in our model that is correlated with the error term. It's just a definition. So let's just put a pin in that for a minute and ask, well, how can that possibly happen? One way that endogeneity can occur is something called omitted variable bias. And you may have heard of this one at some point during a regression class somewhere. Omitted variable bias happens when we have two predictor variables, say x and z in a regression model, and we know that these two are correlated. That's a common phenomenon, right? Multicollinearity or collinearity. That happens all the time. So what happens if we know these two variables are correlated, but for whatever reason we don't observe this one? So I have z, either I've taken it out of the model or I didn't have it in my data set. If z is taken out of the data set, my tendency a year ago would have been to say, well, it wasn't in the model. But now I have to think carefully that that z, if it's correlated with x, when I take z out, z effectively moves from being part of the observed stuff into the unobserved part. It moved, it's still there, it didn't go away, it's just not in my model anymore. So if I take z out of my model, z becomes part of the unobserved part in the error. Well, if my error contains z and I know that z is correlated with x, not surprisingly, x is now correlated with the errors. And that's how this phenomenon can happen. And you're probably thinking, well, okay, well, that's cool, but why is that such a problem? Well, what happens if I have correlated errors, if I have correlation of a variable with the errors, the other parameters estimates in my model become biased or inconsistent, as economists like to say. So this is a problem, omitted variable bias. It can bias the parameter estimates in the rest of the model. So omitted variable bias is one way you can end up with endogeneity. Now let's talk about confounding. This one, if you want to spend a fun day, go find a good, clear definition of the word confounding. I did a deep dive into this when I was putting this talk together, because all I wanted is something I could quote here. So I went through the old Rothman book, the newer Rothman book, the Encyclopedia of Epidemiology, the Encyclopedia of Biostatistics. There's an Encyclopedia of Statistics I have in my office. I went through every econ book I have, which is about 4, and then I went through every epi book I have, which is about 15. I could not find a really clear definition of this in any of those books. The Encyclopedia of Epidemiology, Sander Greenland has a nice entry where he says that Sander Greenland's a famous epidemiologist. He refers to at least 3 different uses of the word confounding. And then I located a paper, and I'm happy to send it to you. I saved it. It's a whole paper on the history of the use of the word confounding in epidemiology. This is a really complicated topic. So the place I finally found a nice, tidy definition that I can use, oddly enough, is in Judea Pearl's book, if you're familiar with Judea Pearl's writings on causality. And this is quoted right out of his book on causality. X and Y are confounded when there's a third variable z that influences both x and y. That's about as tight of a definition as I could find. And I like this because it's saying that z here, z influences x or is associated with x, and it wouldn't be in the model if we didn't believe it was associated with y. So z is a confounder, okay, according to this definition. Well, if z, remember we were talking about z not being in the model, if z is not in the model, z gets bundled up with the errors, so it's an unobserved confounder. And that's a more familiar term. If you poke around with Google and look through the literature, unobserved confounding is a bit more familiar term in the world of public health and in, to some extent, the behavioral sciences. So Z in this case is an unobserved confounder, if you prefer that word to endogeneity. Okay? So how does that apply to our study? We have this GPA example. Well, let's go back through the same exercise with GPA. GPA is equal to, if we're going to fit a regression model, it's equal to all of the possible factors that could influence GPA. And some of those factors are observed factors, but some of those are unobserved. So the observed factors are things like what we have in our data set. We have their high school GPA, their SAT scores, parents' income, sex, those sorts of things. Now, any other day, prior to a year ago, I just would have written E over here and not even thought about it. But let's think about what are the unobserved factors that could influence college GPA. They could be things like ability or motivation. I need to take sleep out because you can't actually measure sleep, but support, emotional support, things like that. How do you quantify those? Those are things that we don't observe, but we certainly believe they exist. If we talk about ability, we sort of think of people like that all the time. Well, that person's really bright. We don't really have a metric. We're not looking at their SAT scores or IQ tests, but we have this impression that they are a person of high ability or lower ability or whatever. So even though we don't observe it or define it well, there are these concepts that we don't observe, like ability or motivation. That person seems kind of lazy, or has in the past seemed lazy, but they're getting better, or whatever. These are things that we don't observe. Kind of like latent variables, if you've ever done structural equation modeling. They're kind of those sorts of concepts. So we have observed and unobserved factors that influence GPA. So let's think about a simple model here. I have GPA, and I think that parents' income influences the college GPA, as does high school GPA. We already saw that those are really highly correlated. So it stands to reason that high school GPA should be in this model as a predictor of college GPA. But let's think about this for a minute. High school GPA and GPA, it's a college GPA, are probably related to this notion that we think of as ability. Okay? Both of those are influenced by ability, and if they are ability, it becomes an unobserved confounder. Okay? So if we have this unobserved confounder ability sort of lurking in our error terms, that means we may have a problem with endogeneity. And so we at least need to explore the possibility that we have an endogenous covariate ability left out of our model. So how are we going to deal with this? Well, one thing that we can do, and this has been traditionally done in the world of econ, is we're going to take our primary equation for GPA, our primary model, and we're going to split off an auxiliary equation. So now we're going to have two regression models. One is for college GPA, the original model we were fitting. The auxiliary equation takes high school GPA and moves it out. High school GPA, remember, is the thing that's related to ability. So we're going to remove it and make it into an auxiliary equation. And we're going to use a variable, we're going to try and find a variable that is related to high school GPA, but is not related to ability. Does that make sense? I tried to color code it to emphasize the notion that high school GPA is equal to factors that are not related to ability and factors that are related to ability. Now I'm starting to see brows furrow. This is where it gets weird. What? This is the part where I started saying, what? That's just, what? Why would this even work? Just stay with me for a second and we'll see how. So what we're going to do is this auxiliary equation. And high school competitiveness is a variable that's in our data set. High school competitiveness probably influences your high school GPA, because if it's more competitive, it's more likely to have a lower high school GPA or vice versa. So it's related to high school GPA, but high school competitiveness has nothing to do with the student's individual ability. So we're fitting this auxiliary model again, splitting it into something, we're using a predictor that's not related to ability, and then we're leaving ability in the error terms. So now what we have are two models, one for GPA and one for high school GPA. And the error terms for these two models both contain ability. There's an error term 1 for the primary model and an error term 2 for the secondary auxiliary model, but both of them have ability bundled up in those errors. Okay, they're both, ability is an unobserved predictor for both of these. So what I'm going to do then is I'm going to take the expected value of high school GPA and I'm going to plug that into my original equation. Okay? And by doing that, I've removed any effect of ability down here. So I've broken that correlation between high school GPA and ability. Kind of makes sense? Sort of? So by using the expected value, so I'm going to fit this model, and the model, once I get rid of the errors, the expected value of this is what I'm going to actually plug in here and use, not high school GPA itself. And that breaks that link with between ability and high school GPA. Well, that's really weird. Okay, so let's think of it again. Let's go through this one more time, but let's look at it as a structural equation model. I've simply redrawn this equation here as a structural equation model, and I've broken the error into two pieces here. I have the just error part for my GPA equation, but I'm also imagining I have this latent variable called ability, and ability, I think, influences both GPA and high school GPA. So now I have this mixture of a latent variable. Are you familiar with structural equation models? Is this helpful or not? Sort of, yeah. So I'll keep going with it.
Well, is this similar, so like with DAGs, like when we use DAGs and EPI?
Similar idea, yes.
Right, okay.
Except I don't think DAGs use latent variables.
Yeah.
I'm
No.
not
And then variables that are in the model.
No, they don't.
It's different.
No, they don't, but I'm trying to imagine this because like with
Right.
a DAG, right, you would adjust for, you might say ability, these are all your unmeasured confounders, this is like your U area, right? And then you're taking high school GPA and you're adjusting for that, saying that this might be accounting for what we're missing because we don't have ability, but
Exactly.
adjusting, okay.
So you're on the right track with it.
Okay,
But this is a structural equation model.
Right.
There are similarities between them. Anyway, so I have this latent variable ability. What I'm going to do by adding in this other variable, watch what happens. When I add in another exogenous variable, to use the terms of structural equation modeling, high school GPA becomes an endogenous covariate, right? You're familiar with SEM? Because now it has an arrow pointed into it. Remember the rule, if it has an arrow pointing into it, it's an endogenous covariate. Well, if it's endogenous, that means it has an error term or residual hanging off the side, right? So now, if I look at this model, I have two separate errors. I have these two models, and I have ability that I think influences both of those, this latent variable. I'm going to do a quick sleight of hand, and it's going to be weird, but I'm going to change this latent variable from a latent variable to just allowing the errors to be correlated and estimating the correlation between the two error terms. Now, this still probably seems weird. The first time I drew this, I thought, all right, this gets me closer, but I still don't understand why this solves my problem. So let me take one more approach at this, and let me see if this helps. I've drawn the two auxiliary equations as a structural equation model, and I've written ability as part of both of these error terms. So now imagine that these two, if I move them together like a Venn diagram, I have overlapping errors. I have something that's overlapping in both of these error terms. And what is that? That's covariance or correlation. I haven't put in the correlation term. That's the thing that made the light go on for me. Because I have error terms that have common covariance. Okay? So that's why this correlation is in the model. And when I do that, in fact, I've drawn this as a structural equation model. I can fit this as a structural equation model using stated structural equation modeling builder. I can actually estimate all of those coefficients and correlations and so forth. So I could do this using a structural equation model. Or I could use this using Stata's new eRegress command. So what I'm going to do with eRegress is I'm going to have this primary model. So the primary model, GPA is the dependent variable. Income is one of my predictors. And then I'm also going to implicitly include high school GPA in my primary model. I haven't written it in here. I could if I wanted to. I probably should. What I'm going to do is then fit a secondary auxiliary model where high school GPA is the dependent variable. And then I'm going to use high school competitiveness as a predictor, one of those fancy predictors that's related to high school GPA but not to ability. And I'm going to include income in there. I could put other covariates in there if I want. What are the predictors of high school GPA that are not related to ability? And that's my auxiliary equation, and I fit that using the endogenous option. So the command is eRegress, and if I have one of these endogenous variables in there, I just use the endogenous option. And when I fit the model, the output then shows me two sets of coefficients. The top set of coefficients is where GPA is the dependent variable. And then I have my coefficients for my secondary auxiliary model, is high school GPA dependent variable model. So I get the coefficients for that as well. And then at the bottom, I also get estimates of the variance of the error terms for the GPA model, the variance of the error terms for the high school GPA model, as well as their correlation. So let's zoom in on this for a minute and we can look at this. The correlation between the errors for high school GPA and, high school GPA and college GPA, that correlation is 0.75. Okay? That's a pretty high correlation in terms of its effect size. And the p-value in this case is 0.000. What this is telling me is that there is correlation between these error terms, which is by definition endogeneity. We're back to just the definition. So what this is telling us is that we do have this problem of endogeneity. High school GPA is correlated with the error terms, and we need to fit this sort of a model as opposed to our plain old linear regression model. Yes?
What magnitude of correlation is big enough?
I don't know. That's a good question, and I don't have a good answer because that's one of those rules of thumb things. Some people like 0.4, some people like 0.6, some people, I mean, it sort of depends on what you're measuring and what field you're in. So I don't have a good answer for that as to what a good cutoff is, but I'm not even sure there is one. Anyone have a good suggestion? Or have read a rule of thumb somewhere that I just have missed?
I've got to update my rule of thumb book.
There is a book called Statistical Rules of Thumb.
Oh, really?
And I stumbled onto one of them on my own, and it turned out it was in that book. But it's another story. So what this is telling us is that, yes, we do have a problem with endogeneity, and we need to build this sort of a model. We can't just use traditional ordinary least squares. What I've done here, I don't know if you're familiar with Stata. After you fit a model, you can type estimate store, and it will store temporarily whatever the results of your model are in memory. So I've done that after each of these models, and here I can type estimates table, and it will show me the coefficients from each of these different models. So remember that first naive model that I fit where the coefficient on program was negative? I just had the program. That one was negative. That's this univar model. The one that the naive model where I adjusted for high school GPA, remember it had the program coefficient was about 0.2, it flipped. So that's this other model here. The model that I just fit using eRegress, I'm calling it Endog. And that's this column right here. And notice that the parameters are changing. Whether they're better or worse or not, we don't know just yet, but they are changing. They are different than what they were before. So we're just going to kind of keep track of these models. So if you're familiar with the jargon of econ, high school high school competitiveness is what's called an instrumental variable. If you've ever heard of instrumental variables regression, that's all we just did. I just didn't use the term endog. And they also use historically have used a different way of estimating this called two-stage least squares. So the idea, if you were doing two-stage least squares, is you fit this model first, you use ordinary least squares to fit this model, and then you take the expected value from here, the predicted high school GPA, and use that as the predictor in your second model. It's a technique called two-stage least squares, and high school competitiveness is what's called an instrumental variable. Tried and true has been done in the econ world for decades. It's nothing new or exotic. We're just using it in a different way outside the world of econ. Okay, so any questions up to this point about endogeneity? Yes?
So it's sort of related to the question I just asked, except now it's this endogenous covariate or instrumental variable. It shouldn't be associated with the outcome of interest. So what if it is, even a tiny bit?
Then it's not really an instrumental variable.
How much is too much?
Yes, tough
It's in the rules of
question.
thumb.
Well, these are all issues, and you're raising traditional concerns about this. What if it is slightly related? These are all judgment calls, and that's part of the, people say Bayesians, it's subjective because you have priors. Well, these are all sort of somewhat subjective judgment calls you have to make along the way as well. What if this correlation was 0.3, and this p-value was 0.048, or well, let's make it on the other side, 0.051.
Yeah.
So it's not quite significant. It's 0.3, is that big or not? Do I have a problem with endogeneity? Or, here's the other problem. What if I didn't even have high school competitiveness in my data set? Remember, these are observational data. I didn't get to pick what's in my data set. So I may not even have an instrumental variable, a usable instrumental variable in my data set. So I admit I've made this look a lot easier than it is in practice. Yes?
And then the identification of the instrumental variables is going to be based on some type of review of the literature and/or theory that you're working with?
Theory and intuition, or prior studies, or
Luck.
yeah, or luck that you even have of such a variable in your data set. What I've done here is I've made something that's very, very complicated look very, very simple. So mostly just to explain the concept to you. But all of these questions are traditional, legitimate concerns when you use instrumental variables. Do you have them? If you do have them, are those still correlated somewhat with the the other thing, likability. Someone asked the question yesterday, I just did this talk at Columbia yesterday, what if you have to have a fairly high GPA, high school GPA, to get into a more competitive school? Or what if your parents make more money, so they got you into a school district where you're in a more competitive school, and these things are all related, that maybe that's why you have your higher ability. There are all kinds of things that, if you think about this too long, complicated, it muddies the water, but that's to some extent the fun of doing real research, because you do have to think these things through and tease them apart. It's not nearly as simple as what I made it look just now.
But it seems like you could also use this to kind of parse out the influence of things that are highly correlated with each other as well. For example, like if you wanted to look at the role that, if you wanted to determine the role of heroin and cocaine used separately, because that's what I study, on some outcome. Well, a lot of people speedball, which means they use heroin and cocaine together, but then you also have people who only use one, only use the other, or whatever the case may be. So it seems like you could use this correlated error terms to begin to try to piece out the contribution of each of those to whatever the outcome is as well.
I think so. I don't see why you couldn't use it for that. Absolutely. You just reminded me of something else. This is not part of your question, but it reminded me. One of the questions, anybody subscribe to SEMnet? It's like a listserv thing for people who do a lot of structural equation modeling. One of the questions that pops up on that listserv occasionally is, when and why would I use correlated errors? You can do that in structural equation modeling, but why would I do that? It's not necessarily that anyway, it's this endogeneity issue. If I think that both of these things are correlated in some fashion, then the errors are likely to be correlated as well. So this comes up in the context of structural equation modeling. People would draw a structural equation model like this and not even think that they've used an instrumental variable. They would never even think of that term. But in fact, that's what high school competitiveness is to an economist. To an economist, if I rewrote this as an equation, they just see simultaneous equations. They don't think in terms of structural equation models. So what I'm trying to do here is show that these concepts actually leap across several fields, and we use different words and concepts for them, but they're all the same. We're getting at the same thing. So, and I tend to think in terms of structural equation models more than the IV-RIC approach. Any other questions? Yeah.
What if there's more than one indigenous covariance?
Well, we're going to see that shortly in a special case, but if you have multiple endogenous covariates, you can have bunches of these. I don't know that there's a limit on how many endogenous options you can put in here. So if you have multiple endogenous covariates, you could control for them all in theory, both in theory and with the software will allow you to do that.
What impact does that have on power?
My humble understanding, keep in mind I'm a novice on this, I'm not an economist, but my understanding is by doing this approach, you're gonna expand your standard errors a little bit on the original variable. Because what I'm doing is substituting in the expected value of high school GPA back into this thing up here. And by building this model, when you take into account the whole model, the standard errors get a little bit larger. And then the question is, how much larger do they get? And what does that do to power? I think that's going to depend on several factors, like do you have any missing data? Or is there missing data in any of these things? Because if you do, case-wise deletion, you just lost some data in here. So there are a lot of factors that go into what it does to your power. But assuming you're not dropping out data by putting in variables that have some missingness or anything, I think you just lose a little bit of efficiency because of this technique, sort of a two-stage approach to it. As to the magnitude of that, or is it a big problem, I don't know. Then, I hadn't thought of this until you mentioned it, then you have the problem is the loss of efficiency worse than the bias that you incur for having the endogenous. If only research were simple, why can't we just use OLS for everything, right? But wait, it gets worse. So, non-random treatment assignment. Remember, we didn't randomly allocate these people to the treatment group or not. So, in a perfect world, students would come in their freshman year, and then we'd see them and we'd say, we toss a coin, and the coin lands head side up. They're in our study program. Another student comes in, we flip the coin, it lands head side up, they're in the study skills program. Another one comes in, tails, you get the idea. Ideally, if we could randomly allocate students to the program group or the non-program group, we would wash away whatever, you know the drill, you would wash away all those other potential confounders. Maybe this group is older. Nope, they were randomly assigned. Maybe that group was the smarter kids or something. Oh, no, they were randomly allocated. By the way, random doesn't necessarily mean representative of two groups. You can have screwed up randomization, but we're going to pretend that randomization works perfectly in this case. So if we could do this, we'd be kind of back to our t-test scenario. But that's not what happened in this study. In this study, students come in and we're like, hey, we got this cool study skills program. Want to join? Sure, okay, I'm not doing anything else. Next person comes in, yeah, I thought he was kind of cute, so I'm going to go too. And then another person comes in, I don't have time to do that. But you get the idea. People are self-selecting into the treatment group or not. And anytime you allow people to self-select in, then you have to start thinking about what are the reasons why someone would self-select into the treatment group or self-select into the non-treatment group. One of the classic examples of this is pregnant mothers. You can't randomly allocate mothers to smoke and not smoke and then weigh their babies. But what you can do is try to model what are the things that influence a mother to smoke. Anyway, we're back to that scenario here. Why did some of the students self-select into the study skills program and not? Well, one way to deal with this is to model the choice to participate or not. The problem with modeling that choice is we're again probably going to run into this endogeneity issue. So we're going to build a side model, an auxiliary model for the student's decision to self-select into the study skills program or not. And that decision is based on observed factors and again these unobserved factors. Well, if we put program in our main equation, so we're back to GPA, is our primary equation, and we would like to include program status in our regression model, we have to take into account or think through, is the decision to participate in a program, is that influenced by ability? Remember, we just went through this whole thing with high school GPA. And if you think about it for a moment, a student's ability probably influences their choice to participate in the program or not. If I didn't do very well in high school, and I feel lucky that I even got in, I'm probably going to look at that study skills program and go, yeah, I probably better do that. I was lucky to get here. I don't want to get kicked out. I'm going to go to the study skills program. Alternatively, students who did really well in high school or students who are of higher ability in general, they're maybe more likely to say, yeah, I got this. You know, I did fine in high school. Maybe later on if things get weird, I'll try it. But for now, no thanks. So your ability, whatever ability is, this unobserved characteristic, may be influencing both your choice to participate in the program and your final college GPA. So we have an endogenous treatment variable. So how are we going to deal with that? Well, we're going to play the same game again. We're going to take program, this auxiliary equation, and we're going to try and find an instrumental variable for program. So in this case, I'm going to use a strictly needs-based scholarship as an instrument, or this variable, because scholarship money, I would think, would be related to choice to participate in the program. If I got more scholarship money, I probably don't have to work as much, and I might have more time to participate in the study skills program. At least that's the argument that I'm going to make. If you didn't get as much scholarship money, or any scholarship money, I might have to spend more time working and less time free to do something like a study skills program. Anyway, so needs-based scholarship money could influence my decision to join the study skills program, but it's not related to ability, again, because it's a strictly needs-based scholarship program. So I'm going to do this again, and this time I've drawn it again as a structural equation model, so now I have this probit model. This is oh, by the way, these are economists, so everything's probit, not logit. So I'm going to fit a probit model for the choice to be in the study skills program. I'm going to use scholarship now as this instrumental variable that's not related to ability but is related to program. And I'm going to allow these errors to be correlated. Same exact thing that I did before. The only real difference is that this now is binary. I'm using a probit model for it. But the logic is the same. So I can use the eregress command again to fit my primary model. I still want to take into account the endogeneity of high school GPA, but now I also want to take into account program and the endogeneity of the program. Now the options are slightly different here. I could use the endogenous option here and put comma probit down here somewhere. And that would be fine if this was just any old binary variable in here. But this one's special, and that's why I've used the option in treat. This one tells Stata, pay special attention to this one. This one's my treatment variable. I want to know what effect that thing has on college GPA. And we'll come back to that down the road for using things like margins and margins plot and E-stat T effects. So by using the in-treat option here, that tells Stata this one's special. This is a special binary variable. That's my treatment variable. So then I fit this model, and now I have 3 equations. I have my primary equation, which is GPA, the thing I'm interested in. And then I have my 2 auxiliary equations. One is a probit model for program. And keep in mind that these coefficients are probit coefficients, so you have to interpret them as such. And then I have my auxiliary equation for high school GPA here at the bottom. And lastly, I have my variance and correlations here. So let's zoom in on that for a minute. Still have my variances for the errors for GPA and high school GPA, but I don't have one for program. I fit a model, that auxiliary, that probit model for program, but I don't have an error term in there. Anybody know why that is? Top of your head? I just don't fit probit models. Probit models, the error terms are constrained to be 1. And so we constrain them to be 1. So even though they're constrained to be 1, I guess we could put that in there. The variance would end up being 0. Well, the variances themselves, that's not too confused. But you can still calculate the correlation between those constrained errors and the errors for the GPA main equation. Okay? So I've estimated that correlation, and this one's lower. The correlation between the program equation and the GPA equation is 0.45, or the errors from each of the equations. And the p-value is 0.000. It's statistically significant. So back to your question, is 0.45 high enough? Is that high enough to cause concern? Do we consider that a problem of endogeneity? Well, we're going to stipulate that it is, because this is a talk about that stuff, so we're going to move along assuming that it is. So we're going to say that we do need to fit this sort of a model if we're going to include program in our overall model. So let's look at our table now of what we fit so far. So we had our univariate naive model where the effect was negative. We had our naive model adjusted for high school GPA, and it suggests that there's about a 0.2 GPA, 0.2 grade point increase due to our program. With this model, treating program as an endogenous treatment effect, the effect is now 0.3 in the positive direction. Okay? So that's about a 50% increase in the effect of program on the final GPA. So any questions about that? We're not done yet, but any questions up to here? We basically did the same thing we did before, except this one's binary, and so we used a probit model. Okay. One more thing to deal with. Okay.
Yeah, so instead of, using that variable as the instrumental variable, could you use a propensity score that, predicts the assignment?
Oh, I don't know. That's an interesting question. I have no idea.
It would be a cool way to do it.
Yeah, because propensity score matching is another popular way of dealing with it.
But here you're using it as sort of an instrumental variable.
Yeah, but this has the added twist of it's an endogenous treatment variable. It's not just a treatment variable that was not randomly assigned. It also has this endogeneity issue with ability. By the way, there's nothing that forces you to. There is an X treat, right? It's just treat option here. In treat tells say that this is an endogenous treatment effect, and you're going to put some other things in there. It's either X treat or just treat, where you tell this is a treatment effect, but it's not endogenous. You don't have to deal with all the things. But propensity score matching would be an interesting approach to this. I have no idea. That's a good question. Put a doctoral student on it. Anybody need a dissertation project?
Would there be a possibility that endogenous covariates might correlate with each other?
That's a possibility as well. And we haven't, I'm leaving out, I've made this, in fact, nobody asked. There's a no interact thing in here that keeps this from getting way out of hand. And by the end, you'll see that there are all kinds of interactions and strange things you can put in here. I've just tried to pare this down to as absolutely simple as it can get, just so we can wrap our heads around the basics, and then we can talk about some complications towards the end. So, was there another question? Did you?
Yeah, sorry.
Okay. All right, so last but not least, missing not at random, MNAR and selection bias. So, ideally, remember we were missing 208 values of GPA. Ideally, these students would come in as freshmen, they would go along, take their classes, and they would all graduate, okay? That would be the perfect world. So we would have a complete sample at the end of all of their college GPAs. But in fact, that's not what happened here. We're missing some data, and there are various mechanisms by which these data can become missing. One of them is called missing completely at random. And this means that the students are going along, and then something completely random happens that keeps them from appearing in our final data set. So maybe this student won the lottery. Actually, while I was working on the slides for this, I had this already in, and like a week later, some kid in Florida actually won $500 million. And, because the headline said college student wins $500 million. So chances are he didn't go back to class and graduate. So we are missing the final college GPA for this student. But because it's completely random, our sample size shrank a little, so we're going to lose a little power, but chances are those kinds of missingness are not going to bias our sample in any way. Because this person's GPA is not likely to be lower or higher or middle, it's just randomly missing. If that's how all the data were missing, it would reduce power a bit, but it's not going to bias our sample in any meaningful way. Missing at random is a subtly different thing. So this means that the students are going along, and somebody drops out. But the reason, for example, this student says, oh, my mom lost her job, I can't afford to pay my tuition, I'm going to have to drop out. Now this is called missing at random. The terms are very unfortunate, I know. It's missing completely at random or missing at random. The difference here is that mom lost her job. Income, parents' income is a variable that we do have in our data set. And so if we have data that are missing at random and it's related to something else in the data set, we might be able to use multiple imputation to sort of get back. You don't really fill them in, so to speak. But we could use multiple imputation and deal with missingness in that fashion. And so we could get our data back, or there are other ways to deal with that, but it's not as big a deal. Unfortunately, we may have to deal with the worst of all of these, which is called missing not at random. So in this case, the students are going along, most of them graduate, but some of the students just struggle and they say, you know, this is too hard, I just give up. College is not for me, my grade points are awful, they're probably gonna kick me out anyway, so I'm just gonna go ahead and drop out. The problem from our point of view is that if students who have low GPAs are the ones who drop out and we never see them at the end, then our final sample is likely to be biased upwards, right? Because we didn't observe that lower tail, or the complete lower tail of the GPA distribution. And so that could bias our sample. And so that's something that we need to at least think about and possibly deal with. So how are we going to deal with data that are missing not at random? One thing we can look at is just, it doesn't matter if they graduate or not. These people, some did not graduate. That's not what we're going to deal with, that's the problem. How we're going to deal with it is, once again, we're going to build a model and take into account the possibility that we have this endogeneity problem again. So we're going to build another auxiliary model for whether the students graduated or not. Again, graduation is a binary variable. We're going to use probit because these are economists that developed this. So we're going to build a probit model, and the things that predict whether you graduate or not are both observed and we have unobserved factors. So I know this feels like a rerun. This is the third time you've seen variants of these slides. But it's the same idea. I'm going to use, in this case, roommate. Whether the student's roommate is a student or not. And that, I'm going to make some really weak argument that influences whether or not you graduate. And it's not related to ability. Whether your roommate is a student or not shouldn't be related to ability, and so I can fit this auxiliary model. But in this case, the auxiliary model is related back to the main model in a slightly different way. Notice that this never goes back into the original equation. That's what's a little unusual about this one. So if I draw it as a large structural equation model, as I did before, notice that I'm allowing for correlation between the errors, but there is no direct relationship back from probability of graduating back to GPA. And that's what makes this a little bit different. Okay? All I'm doing is fitting an auxiliary model and allowing the errors to be correlated back with the main model. So that means we have a third variant of this option, and this one is called select. Select, if you use this option, will fit an auxiliary equation, but it does not put a direct relationship back from that probability of graduating back to GPA. So in that case, I would want to use the select option. So if I fit this model, I still have my primary equation. I have 3 auxiliary equations now. My output is getting really hard to read. So I still have my primary equation at the top, 3 auxiliary equations, and now I still have all of this correlation stuff at the bottom. Again, because the graduation, that model is a probit model, I'm back to using the constrained variance of the error terms, and so I don't see the variance of that model in the top. But what I do get is a correlation between the error terms from the graduation model and the errors for the main GPA model. This time the correlation is 0.6, p-values of 0.000, whatever. And so this suggests that I do have a problem with endogenous selection. So what was that? That was one of the hardest to struggle with, and I get this question a lot, so I'll just ask it again for you. Why does just fitting this other model and correlating the errors, why on earth does that have any effect on any of this? I haven't answered that question for myself to my own satisfaction. All I do know is that it does work, and it's actually a thing. It's called Heckman selection. Anybody heard of Heckman selection? James Heckman won a Nobel Prize. This is 50-year-old stuff, and he won the Nobel Prize for economics for this, I don't know, 30 years ago or something. So anyway, all this is Heckman selection. There's a Heckman command in Stata, and you can do this sort of thing. I don't have a good explanation. Maybe one of you can explain it to me as to why simply fitting that model and correlating the errors deals with missingness not at random, but it does. And at least you convinced the Nobel Prize Committee that it does. So now I have this, as I said, this very large model, and this suggests that I need to fit this sort of model. Now let's take a look at, we had all these other models we fit before. Our final model here, the one we just fit, that takes everything into account. The effect, the treatment effect of our program, study skills program, is about 0.3, which is about what it was here. That didn't change a lot. What did change is some of the other parameters in the model. Now, we'll pull back the curtain and show that this is the equation I used to actually simulate these data. That's partly why I wanted to simulate these data, so that I could show you what happens if you don't take these things into account. You don't get back the original parameters if you knew the truth, which you never do in real life. In real life, you don't know what the real parameters are. But if you do have these issues, these are the coefficients that were used to create the artificial data set, and these are the coefficients that are estimated for that model, and that particular model reproduces or gives us back our original parameter estimates better than the others. So we're not getting these biased parameters. So it works. I put some great artificial data, we get the same thing back. Now, other things you can do with this. If you've used Stata much, you're aware that we have this, what we call an estimation, post-estimation paradigm. So you fit your model first, but then after you fit your model, you can go back and do a bunch of fun things with it. So for instance, there's an estat tfx command. You can use margins and margins plot. If you haven't used margins and margins plot in Stata, go play with those today. These are two of the coolest commands in all of Stata. And then you can also use the predict command. So I mentioned there's that entreat option for the auxiliary equation, and that was special. By using the entreat, that tells Stata if I type estat treatment effects, it's going to find what is the effect of that binary variable on the outcome. Okay? So it's asking the question, what is the causal effect, so to speak, and we'll come back to that word causal in a minute. What is the effect of program on GPA? That effect in this case is 0.2976 and change. In this particular case, it happens to be exactly the same as the coefficient we saw in our model. But that's only because we fit a ridiculously simple equation model. There were no interactions, there were no other things going on, and we'll come back to that in a minute. Or if this was a probit, what if our main model was probit? Here we used a continuous outcome of linear regression. What if we had a probit main equation? Well, this, you end up with these logs and e's and all kinds of things, so this would not be just the basic parameter estimate to get out of the model. So this estat tfx can be a very useful command to follow up your model with. And it's again telling you the effect of participation in the study skills program leads to a 0.3 increase in college GPA. Now, there's another option you can put on this called estat tfx, ATET. That's the treatment and the average treatment effect in the treated group. And that's getting at a subtly different question. The original question was, what's the difference between the two groups? But by adding this option, it's only calculating the treatment effect among the treated. And that's a subtly different question. The question isn't, what's the difference in the two groups? The question here is, what would the GPAs of the students been had the students who took the program, what would the effect have been had they not taken, those same students not taken the study skills program? And that's different than saying I have two groups, what's the difference between those two groups? This is saying, of the treated people, what would their GPAs have been like had those same people not taken the study skills program? So that's the question you're getting at by using this ATET option. You can use margins and margins plot after these models. but you need to read the manual. There's no way. We had to actually add in some new machinery to margins to deal with these kinds of models. So I'm just putting this in here to show you that it can be done, but you're going to have to write out your margins commands very carefully to do these. Now, one of the questions that popped up for me when I was working on this is, I keep drawing these as structural equation models. Why don't I just use the GSIM command? And I asked that of the guy that wrote this, who spent 4 years writing this. Like he didn't think of this first. So I asked him that question. He goes, no, you can't do this with GSIM. And I said, look, but I can draw this with GSIM. He's like, yeah, but there are things you can't do with GSIM that this will. So I didn't believe him, and I spent a whole day trying to reproduce this because I thought, clever. What if we just put a latent variable here? These are constrained. I could put a latent variable and point it back at this model, this variable, and I could constrain that to be, I could do, GSIM won't let you do that. So what I've drawn here is everything you see drawn in black could be done with, say, this GSIM command as a structural equation model. The stuff you can't do is in red, and that is these. You cannot, GSIM will not let you put in latent variables and then constrain them to be something and then correlate them back with other errors. It won't let you do that. That turns out to be a computational complexity that necessitated us building a whole other estimation engine to fit these sorts of models. So these are like GSIMs. In fact, you could almost think this is a leap beyond GSIM. If you've ever used our GSIM command, it lets you fit these crazy structural equation models with binary endogenous variables and continuous endogenous variables and all kinds of things. So you cannot do this with GSIM. You can get part way there, but you can't get all the way there. You can do this with continuous outcomes like we just did with the eRegress command, or you can do this with interval outcomes. And one could argue that this should be an interval because it's GPA bounded between 0 and 4. So if you wanted, you could actually fit this using eIntReg, which does interval outcomes. If you have binary outcomes, you can do eProbit, sorry, no eLogit, again, economists. And if you have ordinal outcomes, you can do eOprobit for ordinal outcomes. By the way, your treatment variables, I used a binary treatment variable, but you can also use ordinal treatment variables. So if you had staged, you had, instead of did you get the treatment or not, you could say did you get no treatment, a little treatment, or a lot of treatment. So you can have more complex treatment variables as well. The question earlier about correlations and things in here, you can have polynomials of endogenous covariates, interactions between endogenous covariates, interactions between endogenous and exogenous covariates. So you can interact all these things and do polynomials in crazy ways that make them far more complicated, and that's when that eStatTFX command really comes in handy, because it'll tease through all of that and get you just what you want is what is the effective treatment on the outcome. Now, I was mentioning this earlier, I like to put this cautionary note at the end. There's nothing in the math or the software that makes these relationships causal. If you have theory, if your science says, okay, these relationships would be causal, if I can assume that I've taken everything into account, if I've accounted for, my treatment was not allocated randomly, but if I've built an auxiliary model that accurately and completely takes into account all of the factors that influence who chose to participate in the treatment or not. If I can make those sorts of arguments from a theoretical point of view, the machinery will estimate the parameters for you. But I have actually heard people say this about both SIM and this, that, oh, well, I was going to use regress, but I wanted a causal model, so I used eRegress. It's like it didn't become causal because you changed commands. It became causal because of the approach you took and the way you thought it through, and then you use some of these tools like SIM or eRegress to estimate those parameters. But at the end of the day, it's not the math and the software that does it. It's you that generates the causal argument.
Just made it up.
So thanks for coming. More questions? If you have other questions later on, shoot me.